Okay, let's talk about experiments. If you want to pause to write this out in your notes for an outline, go ahead and do that now. So when I say the word experiment to you, you probably think of something like this with these Bunsen beakers and people in a lab with lab coats, and that is an experiment, but it isn't the only understanding of the word experiment. The purpose of an experiment is to test the impact of a treatment or intervention or manipulation on an outcome, controlling for all the other factors that might influence that outcome. Within an experiment, you can test research hypotheses. You can observe differences between or across groups to see if a proposed hypothesis holds or not. In an experiment, the independent variable is that treatment or intervention or manipulation, the causal variable, right? The goal of an experiment is to establish cause, so that we say, okay, it's definitely this thing that caused this outcome because everything else was controlled for. And in social justice research, experiments are really great for studying the effects of an intervention. And we'll talk about that in a minute. So variables, we've talked about this before, but specifically within an experiment. An independent variable is the cause or the predictor variable. It's the thing that is manipulated or somehow introduced into the setting by the experimenter, and it has to come first. The dependent variable is the outcome variable or the effect. This is the variable that's measured. The independent variable is not always measured. It's the variable that the researcher thinks will be affected by the independent variable. An experimental or treatment group is the group that actually receives the treatment. The control group is the group that doesn't get the treatment. And then we have extraneous or third variables. These are other variables other than the independent or dependent variables. Control variables are extraneous variables that have not been accounted for by the researcher. And confounding variables are extraneous variables that have not been controlled for. So let me give you an example using these terms. So imagine that we were interested in studying how a mindfulness meditation practice was going to impact academic performance on high school students. In this case, the independent variable in our experiment would be the mindfulness meditation treatment. We would be the ones introducing it. We would be telling them you need to do this 10-minute guided meditation before you do your homework, okay? So the dependent variable in this case would be the academic performance of the students. How might we measure that? Well, their grades before and after the treatment, for example, or their grades on a particular test. So what's important here, though, is that we need to have a treatment group. We need to have high school students who are going to do this 10-minute meditation. And then we need to have a control group. We need to have some of these high school students who are not going to do this meditation. And we're going to measure the dependent variable for both groups, because we anticipate that the students who do this meditation are going to have improved grades. And we have to assume that any other weird thing that might happen would equally affect both the experimental group and the control group. So the extraneous variables in this experiment could be all sorts of things, like maybe some of these students already know how to meditate, or maybe some of these students are more motivated to get better grades than others. Maybe some of them have higher stress than other students. So as researchers, we will try to control for these variables by checking that these various extraneous variables are the same for the control group participants and the experimental group participants. So we might ask them, like, what's your previous experience with meditation? How stressed are you? How much do you want to improve your grades in this class? We'll ask all those things to control for them later. Control variables that are accounted for would be things like age, gender, academic history. And again, we could control for these things to see if they have any impact and if they are similar in the two groups. Confounding variables, these are variables that we can't control for, would be things like the student's access to resources outside of school. Like maybe some of these students have tutoring. Also, family background or the student's household socioeconomic status. All of these things we know will affect the student's academic performance, but we can't necessarily control for them, right? And they will impact the results of the study. So in order to deal with this, we need to make sure that we assign these students randomly to the treatment experimental group or the control group, so that if there's any of these effects, like having a tutor, etc., it should be evenly distributed to the two groups and thus not have an impact on our experiment. If you want, now that you've listened to that, pause and go through and read the definitions of these variables again and see if that might help. So, experiments have a particular logic to them that allow them to meet the requirements of causal inference or causality. So when we say causal inference or causality, that's just saying that we're quite sure that it is this thing that caused the other. Well, how does that happen? The first thing is association. That we know in an experiment that the independent and dependent variables should co-vary in some way with each other, that they are related to each other. When one goes up, the other goes up. When one goes down, the other goes down. When one is present, the other one goes up. When one is absent, the other one goes down. There's some relationship. This is determined by whether the experimental conditions differ significantly on the dependent variable. So we'll see if the dependent variable changed. This is a necessary but insufficient condition for causality because correlation does not mean causation. Just because things are related to each other doesn't mean they're causal, but it's the first thing you need to establish cause. Time order or direction of influence. In an experiment, we have to be sure that the independent variable came before the dependent variable in order to determine that there was a cause then effect relationship. So you have to be certain about the time order. The dependent variables are measured after the independent variable was manipulated or presented. Non-spuriousness. We need to make sure that the relationship between the independent and dependent variables was not a spurious relationship, that it was not caused by a third or somehow extraneous variable. So let's walk through this with our mindfulness experiment example. So in our mindfulness example, the independent variable was this mindfulness meditation and the dependent variable was academic performance. If in our experiment we see that there was a significant difference in academic performance between the kids that were in the experimental group and the kids that were in the control group, we can conclude that there is indeed an association between the independent and dependent variables. But again, correlation does not mean causation, so this is not the end of it. Time order and direction of influence. We need to make sure that that meditation, that independent variable, is introduced to the experimental group before we measure the academic performance. So therefore, we are certain that the improved academic performance is due to engaging in that meditation. The non-spuriousness, to confirm that that relationship between participating in this mindfulness meditation and improved academic performance is not spurious, that it's not because of something else, we have to control for all the extraneous variables that could affect academic performance. As I said earlier, students' motivation to improve their grades, their overall stress level. So we want to make sure that we select participants who are pretty similar, that we test that demographically the groups are the same, and if that difference in academic performance between those who did the meditation and those who didn't still persist after controlling for all those extraneous variables, then we can conclude that that relationship between mindfulness meditation and academic performance is not spurious. Hopefully that makes sense, everybody. If not, pause, read through it again, listen to it again. So a causal mechanism is the process that clarifies what is going on between that independent and dependent variable. It helps to explain why the independent variable is causing changes in the dependent variable. Okay? And a couple different ways that this can happen is one, mediating variables. These are variables that intervene between the independent and dependent. You can see in this graphic here. And that helps explain the causal mechanism. Moderators are variables that make the relationship between the independent and dependent stronger or weaker. So in our mindfulness meditation academic performance experiment, we could identify a possible causal mechanism that explains why this mindfulness meditation might lead to improved academic performance. So for example, one possible causal mechanism is that this meditation reduces stress and improves focus, and that in turn leads to improved academic performance. By reducing stress, this meditation might improve the student's ability to concentrate, and that helps their academic performance. In this case, the intervening variable would be stress. By reducing stress levels, mindfulness meditation intervenes in the relationship between the independent variable, mindfulness meditation, and the dependent variable, academic performance, and explains how that meditation leads to the improved performance. But let's see about a moderating variable. A moderating variable in this case could be the student's prior experience with meditation. If some of the students have prior experience with meditation, they might be more receptive to this mindfulness training, and it might have a stronger effect on their academic performance compared to the students who never did meditation before. So by identifying the causal mechanism and intervening and moderating variables, we better understand the relationship between the independent and dependent variables in this particular model. So we're going to talk about 4 types of experiments. It's important to understand the differences. True experiments are kind of our baseline here, what we kind of judge everything else off of. So I'm often going to be comparing from true experiments against others. So true experiments, they're also referred to as lab experiments or basic experiments. I know it's confusing, but we're going to go through experiments because that's what the book uses. I tend to say lab experiments, but you know, what will be will be. True experiments are typically conducted in a lab-based setting under a high degree of control. There are 3 requirements for a true experiment. 1 is that there's at least 2 comparison groups. 2, that there's a time order that we just talked about. And 3, true experiments require random assignment. Okay, random assignment is important. I don't want you to get confused between random assignment and random selection and sampling. Random selection and sampling is when everybody has an equal chance of being placed in the sample. Random assignment is that people are randomly assigned to either the treatment or the control condition in an experiment, okay? It is confusing, but you have to get it stuck into your head what the difference is. So why do we care about random assignment? Well, random assignment ensures that the treatment is actually what is causing that change in the dependent variable, because there's no differences between the 2 groups as long as they were randomly assigned. Any of these exogenous variables will be equally distributed between the treatment and the control group as long as you randomly assign them. As long as you will test for equivalence between the groups, you're good to go. It's the gold standard. It's not always possible, that we'll talk about in a minute. So let me give you an example of a true experiment in a lab setting. And you probably don't know this, but all over the communications building, there are these little labs that people do experiments in. So imagine that there's an experiment that is interested in understanding implicit bias, okay? So we have people we randomly assign them to two comparison groups. One is an experimental group that receives an anti-bias training, and then there's a control group that receives like a training in, how to use PowerPoint or something. Like they still have a training, but it's not on anti-bias. The time order would be established by measuring implicit biases in both groups, both before and after this training intervention. The participants who were in the group that received the implicit bias training, we should see a change in their implicit bias test scores after the training program as compared to before the training program. And for the people that went into the PowerPoint training, they should not see any difference in their implicit bias scores. So again, we randomly assign people to one of two groups. The experimental group gets the training, control groups gets the PowerPoint training. After the training program, both groups, they have this test that they take, again, an implicit bias test. And then we compare, was there a reduction in biases? So as long as we met these requirements, two comparison groups, temporal, time order, random assignment, we're good to go on a true experiment. So I want to point out to you that there are different kinds of true experiments, and one that's very common is a factorial experiment. And a factorial design uses numbers and crosstabs to visually depict the number of independent variables and the level of each variable, a 2x3 design. So let me give you an example of a 2x2. So let's say I'm interested in temperature of the room and noise level on task performance. This would be a 2x2 factorial design. Two independent variables, temperature and noise level, and two dependent and two levels of the temperature variable. The temperature variable has hot and cold, and noise has noisy and quiet. So the dependent variable is task performance. So there's like a standard test that people are given this sort of like little building a puzzle sort of thing task to do. And there would be 4 different comparison groups. One group is going to be hot and noisy. One group is going to be hot and quiet. One group is going to be cold and noisy. One group is going to be cold and quiet. So we randomly assign people to one of these 4 comparison groups in different rooms that have different noise level and different temperatures. People in every group would do the same little task, and we measure how many errors they do in the task, how long do they take to complete the task, how good of a job do they do on the task. And that factorial design allows the experimenter to look at both the main effect of each independent variable, so across the 4 different conditions, what's the effect of temperature? Across the 4 conditions, what's the effect of noise level? And the interaction effect. What's the one that impacts the most? Hot and noisy, hot and quiet, cold and noisy, and cold and quiet. And that interaction effect reveals whether the effect of temperature on task performance differs by the noise level and vice versa. So this is very commonly done, and you can look at a lot of different things within it. Now, all true experiments have to have some sort of post-test measure that you're measuring something after they had the intervention, where the variation in the dependent variable is measured after the experimental group got the treatment. Here are 3 different kinds of true experiments. One is a post-test only control group design, and this is a case where the dependent variable is only measured after the treatment. I'll give you an example. So imagine that we're interested on the effect of color on memory in kids. In this experiment, we have 2 comparison groups. An experimental group that's presented with some information that's in the color blue, and then another group that's presented with the same information in black and white. The experiment would use a post-test only control group design, which means that the dependent variable of memory recall would only be measured after the treatment, where we present them with this information. So we would randomly assign the kids to either the experimental group or the control group. The experimental group would get this information in red, and the control group gets it in black and white. after they're presented the information, there would be a memory recall test in both groups. So, what was there a dog in the picture or whatever. The post-test only group ensures that the observed difference in memory recall between the experimental and the control groups is due to that intervention of the color presentation and not to any pre-existing differences between the groups. Now the next one is a post-test control group design. The dependent variable is measured before and after the treatment. There's a limitation in that the exposure to the pre-test might interfere with how the participants react to the treatment and the post-test measures. So here's an example. Let's say we're looking at the effect of music on creativity. We have two comparison groups. A group that's going to get exposed to music and a group that's not exposed to music. With the post-test control group design, the dependent variable of creativity would be measured both before and after that treatment, which would be exposure to music. To conduct this experiment, we'd randomly assign people to the experimental group or the control group. In the experimental group, some sort of music would play. In the other room of the control group, there would be no music. And both before and after they're put into these rooms, there would be some sort of creativity measure. So it's a problem because people are already going to be thinking about creativity because before they were put in their room, they were prompted to be thinking about creativity. But, this is somehow how these are done. A Solomon four-group design combines the post-test only control group design with the pre-test post-test control group design. There are 4 groups in total: one pre-test post-test group, a post-test only group, a pre-test post-test control group, and a post-test only control group. So let me give you an example of this. Let's say we were going to do some sort of training on critical thinking skills. With 4 comparison groups, we would set this up as such. People would be assigned to one of 4 groups randomly. The pre-test post-test group would have some sort of training focused on critical training skills, but the post-test only experimental group would only participate in the program and only do a post-test analysis. And the pre-test post-test control group and post-test only group wouldn't participate in the program. Before and after the treatment, critical thinking skills would be measured in all the groups that are pre-test, post-test. The post-test only groups, it wouldn't be measured in. So just some different designs to be thinking about how you set things up. The next type of experiment we'll talk about are called quasi-experiments. So the big thing to remember with quasi-experiments is that they generally don't have random assignment, okay? That is what is really, really important and the big difference here, okay? So they lack random assignment to experimental and control conditions because of either practical or maybe ethical constraints. They're sometimes used also because true experiments are just not feasible. So, for example, maybe a researcher is interested in comparing 2 communities, in Seattle, and one community is receiving a particular program. Those community members were not assigned the community that they're living in, but the researcher's interested in the effects of it, and so they pick another neighborhood in Seattle that's demographically pretty similar as a sort of control group, but again, people were not randomly assigned to it. Also, sometimes there might be ethical considerations that you don't want to withhold something from people, so you will not create a control condition. With these, you can use a post-test only or a pre-test post-test design, depending on how it's set up, and you compare your experimental group to this comparison group, again, not randomly assigned. In quasi-experiments, our claims to causation are made much more cautiously because of the lack of random assignment. There are just infinite reasons why this may or may not occur. A kind of famous communication quasi-experiment was this case of a city in Canada, and it was like near a mountain. And when TV finally arrived to that town, this was obviously a long time ago, one side of the mountain had access to TV broadcast because like the antennas worked, and the other side didn't. So teachers in the schools were noticing that there was a big difference in how kids were working on their homework and being prepared for school. And they ended up finding out that the kids on the side of the mountain that had access to TVs were doing worse in school than the kids who didn't have access to TV. And this is not to demonize TV. I'm just telling you about this study. So obviously it wasn't randomly assigned if they lived on one side of the mountain or not. And they did look into, is like, do poor people live on one side or the other? And it didn't. So this was a really interesting case, a real life case where it wasn't randomly assigned, but still allowed us to see an effect. Is it absolutely certain that it was the TV causing it? No, but does it look like it probably was? Yes. So a pre-experiment is when you can't do a true experiment, you can't do a quasi-experiment. It's sort of like a first step. It's not ideal, but they can be helpful, but definitely our claims of causality are really iffy. So for example, in a one group pre-test, post-test, pre-experiment, there's no control group, but the dependent variable is measured before and after. So maybe they're interested in testing empathy levels after people participated in a workshop on race relations. They measured before and after, but there was no control group. A one-shot case study is without a control group or pre-test, post-test measures. It's not really an experiment, but it's kind of like it. So for example, someone's interested in studying social media use during an earthquake. They can't really collect data before the earthquake because they didn't know the earthquake was coming. And so they're only using post-test measures. They can't compare to a pre-test or a control group. Natural or field experiments are really interesting. These are experiments that are conducted in natural settings. They are great because they have really high external validity because they are in real life, they are in the world. But a challenge is that it lacks all the controls that exist in a laboratory setting where you can, choose everything from the wall color to the noise levels, etc. They can be expensive. You're possibly not getting full consent from your participants, and they're usually not going to be randomized. This also includes interventions like health interventions or other strategies that are designed to create change. They also could include time series experimental studies that are field experiments that look at interventions over time. So you can see the effects of an intervention like in the long term. So for example, if you were trying some sort of new reading program on elementary students, just testing their reading skills, a week after the program is probably not going to be that helpful. But if you keep on measuring it for years, you can really see long-term effects. So health intervention studies are really common. They're really interesting. So let's say that we were going to set one up to have some sort of mental health intervention on campus, and we wanted to reduce symptoms of depression amongst UW students. So we could have an intervention where we had posters around campus, counseling services, support groups, online resources, etc. And we could test it over a quarter, an entire year, a couple years to see over time if there seemed to be an effect. Now, obviously, other things can go on, so it lacks that sort of solid causal argument that we get with lab experiments, but it could be really interesting. So those are the types of experiments. Let's talk about how one actually designs and conducts a study. This is a very simplified version, but I'll walk you through it a little bit. So Obviously, first you got to get your IRB approval and you do your literature review and you have your hypotheses, etc. Let's assume all that stuff is done. You have to recruit participants. In general, experiments almost always have convenience samples. And it is very common for undergraduates that participate in research studies for extra credit. You may have done this in the past. Some departments require students to participate in studies for extra credit. So in general, participants are going to be a convenience sample. And if they're not undergraduates, it might also still be a convenience sample. Maybe you've seen in the bathroom or posted at the bus station or something signs that are like, are you interested in being in a study? You can be in this study and receive so much compensation, some money for participating. So again, these are convenience samples. But importantly, in experimental studies, we're not as concerned about the sampling like we are in survey research and other research studies, because with an experimental study, presuming that you have random assignment, you're arguing that because you controlled for so many things that you're just saying this caused that. So it's not as big of a deal to have some sort of representative sample. So when you're recruiting participants and you are randomly assigning them to conditions, you want to keep about the same number in each condition. And you definitely want to recruit more people than you need for your sample size, just in case something funny happens. So in general, we usually have about 20 participants or 20 items per condition. You get a couple more just in case something funny happens. Your next step is to get consent from them. So in all research studies, we're going through an informed consent process, but with experiments, it's pretty important because people might be deceived about what they're going to be involved in. But overall, in all studies, there's going to be greater risk because people are being exposed to something that they probably wouldn't have encountered in their regular life. So consent processes in experiments are taken very seriously. So then remember, you're manipulating the independent variable, and that could be exposing someone to some sort of stimulus material like a picture or music, maybe playing a game. Sometimes there are confederates, which are research assistants that are part of the experiment. Like there's other people in the room, but like they aren't actually doing the study. But it's very important to always make sure that the strength of your manipulation is good, because if your manipulation isn't strong enough to bring a change in the dependent variable, well, then you have nothing. And there's two different things you want to consider here. The first is a manipulation check, and this is little evaluation within the experiment to make sure that the manipulation worked as was intended. So for example, let's say that the manipulation was you got a picture of someone with glasses or without. There would be a question at the end like, was someone wearing glasses in your picture? And if they were, and the person answers no, they did not, well, maybe there was something wrong with the way they answered. Or maybe nothing happened at all in your experiment. So this is important to do. Also, threshold effects. Sometimes the effect of the independent variable on the dependent variable only happens if the manipulation is really strong. So it's important to pilot and pre-test these things, but these are just things that you look at when you're manipulating something. So remember, random assignment's key. It should eliminate any biases, and you can later test for equivalence between the various condition groups on all relevant details. You can also do these matched pairings, but it's not as good as random assignment. Again, remember, let's not mix up random sampling with random assignment. Control groups matter. You want to make sure that, controlling for extraneous variables is important. There's two threats that we want to think about. One is the Hawthorne effect, and that is that Because a participant is in a study, they might behave differently than they would in real life. So, for example, if you were in a study and you were having to rate the attractiveness of someone, it's one thing when you have a piece of paper in front of you and you have to mark 1 to 7 on a piece of paper arbitrarily. That's different perhaps than the attractiveness rating you might give them in your own mind walking down the street. Also, this is especially true when people are supposed to be simulating real life things. So for example, let's say there was a task where people had to work together on a project. People are behaving in ways and they know that they're being evaluated by some other person, so maybe they're being more polite. There's also experimenter effects that matter, and that sometimes the experimenter can unintentionally influence things. So, for example, imagine that there's an experiment where someone is getting some sort of medical treatment and that they have a placebo, which you probably know is like a fake medication. And the researcher knows that the pill in their hand is the one that really matters. And so when they go to give it to the participant, they're like really excited about it. And they're like, okay, let's hope for the best. Or they go to the person that's in the control group that's getting the placebo. They're like, here's your pill. So one way to deal with this is called a double-blind experimental design, that neither the participant nor the researcher knows what condition or what treatment someone's receiving, so that you don't have those effects. And then you measure the dependent variable. You can do this in a bunch of different ways. Self-report is someone, being asked paper and pencil or on an iPad or something, like on a scale of 1 to 7, how attractive was that person? There's also observational. So it might be, and we have an observational lab in the communications building that is super interesting. And so maybe you did an intervention and then you're watching how people behave. This is especially common with research with kids, that they're not going to be able to answer questions very well, but maybe you gave them this doll and then you see how they behave with it. There's also a growing movement in communication on physiological measures. So seeing how changes to biophysical indicators like heart rate or blood pressure or cortisol, which is like a stress hormone, people will measure these things to see how people change. And this is a really cool new growing part of communication. Also in an experimental study, debriefing that we talked about in the ethics module is super important, because people might feel like that they were tricked somehow, and they should be told after the fact like what the experiment was about, especially if there was deception involved, and let people ask questions about what happened to them. So internal validity is extremely important for experiments, because we are trying to isolate just the manipulation or the treatment as the cause. And so we need to say, was everything else the same? Internal validity is the extent to which researchers can be confident that the changes in the dependent variable are caused by the independent variable, ruling out any other factors. The fewer potential other factors, confounding variables in an experiment, the greater the internal validity of the study. Lab experiments are really high in internal validity, especially because you're doing all the procedures the exact same. They're in the exact same room. The lighting's the same. The person that greets them at the door is the same. Other kinds of experiments that we talked about today, quasi, pre, and field or natural experiments, have far less internal validity. So some things that can impact internal validity in an experiment is this list. First, history. This is the likelihood that some other external event other than the treatment happened between the pre-test and post-test measures that influence the outcome of the study. This is especially important if there's a longer duration of time. So for example, imagine that someone has some sort of medical treatment that they're given, but then at home they also start doing acupuncture. And then they do the post-test measure, and it comes out that, they've improved a lot. Was it due to the treatment they were given, or was it because they went for acupuncture? You don't really know. Maturation is internal factors that are associated with changes in the participants themselves. Maybe someone got sick, maybe someone's depressed, etc. So maturation is just change over time. Testing is an effect that if someone did the pre-test, it can impact their post-test. So we gave that example earlier about if there was an experiment on creativity. By doing this pre-test where you're asked about creativity, you walk into that room already thinking about creativity, and that might affect how you answer the questions on the post-test measure. Or even more, let's say that the intervention was a bias training. Already being asked about your biases before you go into that training is getting you thinking about it. Regression to the mean is post-test scores that tend to be much closer to average or normal compared to the pre-test scores. So this is basically that in the pre-test, there's going to be a lot more variance than in the post-test. Selection threat, this is a really big deal. So volunteering for studies. I was talking earlier about how you see these signs at the bus station or at the bathroom or whatever that are like, hey, get paid $30 to be in this study. People that sign up for studies aren't necessarily representative of the general population. So maybe they're very poor and they need the money so badly, so they sign up for a study. Or maybe someone's super interested in science and so they sign up for the study. Or maybe people are unemployed, so they have a lot more time to be in a study. It's not a good representation of the entire population. And then also attrition. People drop out, especially if studies are a long time. And so this is a bummer, and it's not random. People that are going to quit halfway through are probably people that are busier or have other things going on. So these are all different things that can affect internal validity. Now, external validity and generalizability. Generalizability is researchers asking themselves if the results of their study conducted with the sample that they have could be generalizable to other contexts, cultural groups, geographic locations, and time periods. Would this result make sense in another setting? External validity is whether the findings from the study would be valid in the world in a natural setting. These lab-based experiments do not represent natural settings very well, and they're low in external validity. Like that example of, in a lab, you might rate someone attractive with a certain score, but on the street, it's probably different. Also, lab-based experiments are usually short. That dependent variable is often measured very soon after the independent variable. So you really don't know about long-term effects. It's hard to make an argument about, you know, does this thing really reduce bias when you measured it 20 minutes after the training? There are a couple things you can do to improve generalizability. One, you can make laboratory settings more realistic and more natural, that it doesn't feel so fake. This is hard to do. Field experiments are a good alternative because they allow for observations of behaviors in natural settings. And then also to manipulate more than one independent variable in order to capture how complex communication behaviors are in the real world. Further, as I said, when people are volunteering for these studies and it's a convenience sample, it's not so great. So you could try harder to have in your experiment a more representative sample than what you would normally see in a convenience sample.